We have been working with techniques on how to differentiate integrals using the Lebon's rule. In one of the past videos in this series, we had developed the most general expression for the Lebon's rule. That's this equation here. The playlist for these videos is at the website digital-university.org. If you go there and then click where it says free calculus videos and then scroll down to where it says differentiating integrals, you see the first 3 videos in this series. They were all set up here to help us develop the Lebon's rule, and here is the most general expression of it. Now what we're going to do is use this to solve a specific problem, and that will be this one here. Let's say that we have the integral of the cosine of xt divided by t dt, and let's say it goes from x squared to x cubed. That's our integral, and we want to find the derivative of that integral with respect to x. Now, as you saw us discuss in the previous videos, if we went ahead and integrated this, of course we would just treat the x as a constant, and then we'd have some function of t, and t would get replaced with x cubed and x squared. So this will give us some function of x, and again we discussed that in more detail in the previous videos in this series. What we want to do now is say, if we have this, how are we going to get the derivative of this integral with respect to x? So going now to the Lebon's rule, this that we developed in the, not the last video, but the previous video, the first thing we do is consider this term where we differentiate f of xt with respect to x inside of the integral. So let's just consider this first term right here. So for that term, that means differentiating this with respect to x. So we're going to have the integral x squared to x cubed, the partial with respect to x, cosine of xt over t dt. So we're taking the partial of cosine of xt over t with respect to x, where this is just treated as a constant, so this would just be 1 over t. Then the derivative of the cosine of xt with respect to t, well, the derivative of the cosine is minus the sine of xt, then times the derivative of this with respect to x. That will just give us t. So differentiating this with respect to x just gives us minus the sine of xt. And we have our limits. And now when we integrate this, we treat the x as a constant. The integral of the sine is minus the cosine. We have a minus sign here, so this just equals plus the cosine of xt divided by x. And t goes from x squared to x cubed. So this will equal 1 over x times the cosine. T equals x cubed. So x cubed times x, that's x to the 4th, minus 1 over x cosine Now here we have x squared, t equals x squared times x, that's x cubed. So this expression gives these two terms right here. So this part of our formula gives us two terms here and here. Let's write them up here. So we have 1 over x cosine of x to the fourth minus 1 over x, the cosine of x cubed. So those are the first two terms that we have in our formula that came from here. Now we have to consider this expression and this expression. Let's do that as soon as we make some room. So here, the integral is some function of x and t, just like we have right here. This term then is just that function where t is replaced with this. So we'll do that here. This is our function x of t. Replace t with x cubed. So the cosine. T is now x cubed, so that's x to the fourth. T is x cubed. And then we have the derivative of v with respect to x. That's x cubed, so we have the derivative of x cubed with respect to x. Then we have minus f of xt is f of xu. So now we replace t with x squared. So we're going to have cosine. T is replaced with x squared, that's x cubed. T gets replaced with x squared. And then we have du dx. U is x squared. So this, that's 3x squared. This is 2x. So x squared divided by x cubed, we're going to have 3 times cosine x to the fourth divided by x. That's this term. We have 3 times cosine x to the fourth minus, now here we have x divided by x squared, so we'll have 2 cosine x cubed divided by x. So these two terms we obtained from these two terms, and then from this expression we had these terms up here. So let's write all the terms out together. We'll take these first. We have 1 over x cosine x to the fourth. This is this term, then we have minus 1 over x times the cosine of x cubed. Then we have these two terms, plus 3 cosine x to the fourth divided by x. minus 2 cosine x cubed divided by x. So these then are the terms that we get from applying our formula that we developed a couple of videos ago. This gave us these two terms. This and this gave us these two terms. And we could probably simplify it. We'll have 1 over x times 4 cosine x to the 4th and minus 3 times the cosine of x cubed. And it looks like that should be then the end of the problem. So again, we started with something that might look very difficult to begin with, this integral. Then we want to consider how we could take its derivative with respect to x. But if we just go ahead and apply the formula that we developed a couple of videos ago right here, then we see it's pretty, the handling it is really pretty straightforward. So we have that this comes out to be equal to this, and that's the answer. Now, the real beauty of the Lebant's rule, though, is not just to take derivatives of different types of integral expressions, or can come in very handy, as we'll see in the next video, is we might have some integral of this general form that is so complicated that we can't evaluate the integral. But yet, if we apply Lebant's rule, we can differentiate it. Then once we have the differentiated form of the integral, we can go back and figure out how to integrate the original problem that we had that before we were not able to do. And we'll have several demonstrations of that now in the future videos.